So we're starting with work. Work is the exertion of a force over a distance. If you have, okay, we're going to create our, we're going to have a crate, because physicists love crates. And we're going to push our crate across the floor. Okay. Okay, on the floor we've got, so if we're going to push it this way, we have our force acting in that direction. Over here, we have friction acting against it. Yeah? So we're going to push our crate okay, so we're going to push our crate so that it goes this far. Okay, and yes, the shape of my crate changed, but don't worry so much about that. Got a little squished. Okay, so it travels this distance right here. Okay, this is some distance. It's some change in our x. It's some change in distance. If we push our crate against friction, okay, at a constant velocity, so that means we're not accelerating. So that basically means that this force right here that we're pushing the crate is going to be pretty much equal to the friction. Yeah? You guys follow me there? That if we're not accelerating, then the two forces are balanced.
Yeah.
Okay, but we can still push the crate at that constant velocity because we have to push against the friction. All right. So if we push our crate against friction at a constant velocity, the amount of work we do is equal to the force that we push it times the distance over which we use that force. That is our work. Okay. Now, this has a number of different applications. Okay, let's say we want to lift something. Elbow should be in like that, actually. Yep, sorry. Okay, and this has, let's say this has a mass of 500 kilograms. Because it's, it's Matt over there lifting these weights. All right, so Matt's going to do a clean and jerk, right? He's going to lift his 500 kilograms from here to Okay, he's going to lift it to there. Ta-da! Now when he lifts it, granted it doesn't always work like this, but if you were to lift it this distance, which is probably about 1.5 meters, okay, he would be exerting a force on this, okay, an average force over this time that's going to be equal to gravity. Because the force on this guy is mg, and so to get this to lift, we would need some applied force that lifts it. And once it's here, once it's already up there, we still have mg and F. But he's used this force over a distance of 1.5 meters. So he's gone from here to here. And so the work, because our work equals our force times our distance, or we can call this d, right? Or delta x can be called d. Work equals force times distance. The distance that we moved it is 1.5 meters. And the force we exerted on it is equal to our force of gravity. Well, that's going to be, if this is 500 kilograms, then our force of gravity is going to be 5,000 newtons. Good. 5,000 newtons. Multiply those, and you get 7,500. And that brings us to our unit for work, okay, which is a Newton times a meter, which is equal to a joule. So 1 Newton times a meter, or that's equal to a kilogram meter squared per second squared, is how it breaks down to all the individual ones. Okay, but it's really a Newton times a meter is a joule, and this is a kilogram meter per second squared, and this becomes 7,500 joules. That is the amount of work that Matt would have done when he lifted his 500 kilogram barbell up over his head by 1.5 meters. Yeah? Okay, now there's some cool stuff here. Work, this is one of my favorite terms in all of physics. Work is path independent. That means it doesn't matter how you get from one place to the other, okay, or how far your overall travel is. It's based on where you start and where you finish. I will in a sec. Okay, yeah, so. Okay, we're recording. So, okay. So work is path independent. So let's say you want to lift another crate, and you have this option. Oh, I say it's not a crate. You're going to move a piano. You guys are moving, and you got this big old piano. Well, your task is to put the piano Okay, we need to get this piano into the back of the van. What's going to be easier to do? Push the piano to the van, get a couple guys and just lift it straight up into the van? Or, what do moving vans come with? They come with a ramp. The ramp extends down so you can push the piano up the ramp. All right. So what happens is you exert your force. Okay, there's a little bit of force that you need to put in that direction to make it go up just a little bit, and so you can, to do the same amount of work, piano of mass M, here's our height, H. Okay, to do the same amount of work, you can use a smaller force over a larger distance, or you can do a lot of force times a small distance. Does this make sense? Yeah. Okay, this is why we have things like ramps. Okay, this is why we have things like pulley systems. All right, so check this out. You guys ever seen those really complicated pulleys? Imagine, if you will, that you're back on the ship. Okay, and you're back when they had, in the age of sails, and they had to move things on and off the ship from the dock. And they had these big old arms with the ropes on them and the pulleys. You know what I'm talking about. I know you've seen the movies.
Like a crane?
Kind of like a crane. Like Pirates of the Caribbean, where they're trying to move stuff on and off the ship. All right.
You are, but like
I am an actor.
famous.
Because it's very risky. Your actors are very lucky if if they get paid to act. All right, then you got another one of these up here. All right, this is called a block and tackle. I don't know if you've ever heard of one of these before, but this is a series of. Better color here. We've got a rope sticking down off the side. Sure. Okay, so here's the idea. Rope, we've got all these pulleys, right? It's got rope wrapped around all these pulleys. Okay, to make this make the set. And so you haul up the top pulley, and you have a box, or, because this is physics, we're going to have a crate. Yep. Okay, and we're going to lift this crate into. We're going to lift this crate into the cargo hold of the ship. All right, and so you have one person. If you got the one person, and all he's got for his, if we got it. Oh, I'm sorry, I need to draw a second pulley because we need to show the difference. Oh, forget it. You got one guy, and he's standing above the crate. Okay, and he's just trying to pull it up with a rope, just pure muscle, just one rope sticking off.
No.
All right, so you got this guy standing over here on the side, and He's got a rope. And he's got a rope, and he's just pulling the crate up, just pure muscle straight up. He's going to lift this crate a distance x. Okay, and there's the force, which equals mg for this crate, right? So whatever the weight of the crate is, he's got to just pure muscle it up. Or, okay, you've got little old me over here who, may look like a big dude, but doesn't do a whole lot of physical work. But I'm a physics teacher. And I know this, that if I pull on this with a certain amount of force, okay, we're going to call this little f, not to be confused with friction, just to show that it's smaller. Okay, that all of the force is acting on this thing. If I pull on this force is going to be the same through all of through all of the rope. Okay, this creates a tension, right? If I pull on the rope, we create a tension. That tension is the same throughout the entire rope, all the way through all the coils, which means that there's a tension here, and a tension there, 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 and a tension there. That's 1, 2, 3, 4, 5, 6, 7, 8 tensions. Yeah? Because each rope, okay, and all of them are pulling up on the pulley. But I'm only pulling with one tension down here. So how much more mass can I lift with this system with what I'm pulling here? If I'm maxed out, okay, and I can exert 20 newtons, right? How much can I really lift? Okay, well, if there's 8 strings of rope attached to the pulley, I can actually pull 8 times what my personal maximum force is. Yeah?
So 20 times 8.
Yeah, so it would be 20 times 8. So I could lift 160 newtons. It's really not a whole lot. 60 newtons is about, 60 newtons is about 4 pounds. 16 newtons is, I'm sorry, so 16 kilograms is let's see, it's about 35 pounds. So, all right, so if I could pull 20 newtons, if my max is I could pull 20 newtons, that means I can max pull something that's 2 pounds, that's about 4 pounds, 5 pounds. But if I hook it up to my system here, I can multiply that by 8, and all of a sudden, this makes me a heck of a lot stronger. Okay? And so the weight that I can move can be freaking huge just by standing here on the bottom and pulling. Now, but here's the trick. For every meter that I go this way, this gets divided by 8 because it all wraps around the coil, and so for every delta x here, I get delta x over 8 here. The amount of work I do is the same. I'm still going to move this mass, okay, this distance. Okay, but for here it's going to be tension times the amount of rope that I pull.
Divided by, oh wait, no.
For me, it's going to be the tension times the amount of rope that I pull. But over here, it's going to be 8 tension times
delta x.
its height.
Height.
That's how far I'm pulling, right? So I have to pull a whole lot of rope to get the same, to move this big crate the same distance that I would have to do here. But this guy has to do 8 times the force. You guys, does this make sense, you guys? Okay, so that's what this kind of system does, and the whole idea is this right here. That I found a way to use to be able to do a small amount of force over a big distance rather than a large amount of force over a small distance. Yeah? Okay. Another way to think of it is, how many of you guys have ever ridden your bicycle up a hill?
I've tried.
Okay. Did you have a different gear? No, you had a fixed gear? Okay. You guys ever change gears when you're trying to ride uphill?
No.
Okay.
Like drive.
You go to a lower gear. Okay. That means you have to spin more, okay, on your bicycle pedal to go up the same height, right? You have to spin more, and it's easier to spin than if you use a large gear and you only do it a few rotations. Yeah? Okay, so this is the whole idea of work is path independent. Okay, it doesn't really matter how you move the object, whether we lift the piano straight up or we roll up the ramp. If we full on muscle a crate up into the boat, or we use a pulley system to lift up into the boat, the amount of work that gets done is the same. The crate gets in the boat. The crate gets in the boat. Okay, but the way we go about it is very different. It might tend, this amount of work that I did is equal to this amount of work that happens with the pulley. Yeah? Okay. Now, here's where we go with this. Now we've got our crate up here. Okay, and we've lifted it this height off the ground. Okay, somehow we had to use, if we were to just muscle it up, this would be the force. We'd be acting against the force of gravity, and so the force of gravity is what on this thing? If this has a mass of m, okay, the force of gravity would be mg, right? Equals the force of gravity, and we move it up this height h. Okay, that means that the amount of work we've done is going to be this. It's going to be our force times our height. I hope you guys are getting this down. You don't need that in your hand right now. Okay. So, what would happen if I cut the line?
I'll fall.
It would fall.
That's exactly.
Would you be more worried if I cut the line if it was up here or if the crate was down here?
High up there.
Up higher, right? So, which of these variables changes? It's the h, right? Okay. So, have we talked about this one before? We may have talked about this before. Okay. Well, this winds up being the amount of work that you do when you raise an object into, when you lift an object up. Okay, is mgh. Okay. There's another equality to it. Well, we'll get to that another time. Here's work. We're going to stop here, and we're going to do a little demo here.